All right, good morning, everyone. Please be seated. Our first talk is just about to start. So our first speaker today is Luciano Ramalho, and he is going to be talking about sets. The talk is titled Set Practice, Learning from Python Set Types. So please give a warm PyCon welcome to Luciano.
Thank you very much, everyone. Thank you very much, Maras and the PyCon organizers. I love this conference. Have made many friends over the years here. So I am Luciano Ramalho. I am a principal consultant at ThoughtWorks, a company that has offices around the world. It's an American company that has offices in many countries, and I live in Brazil, and I work in their São Paulo office. So I'm better known in the Python community these days because I wrote Fluent Python, and that's the Chinese edition that I learned only a couple months ago, has already sold 30,000 copies in mainland China, and there's another Chinese edition in Taiwan, and 7 other languages where it's available, so I'm really happy that the book is a success and people like it. And I want to tell you that I'm working on the 2nd edition. I signed the contract with O'Reilly to do that. And my goal is to get it finished as soon as possible after Python 3.8 is released. The Python 3.8 release is scheduled for October. And so my idea is to get done by October, November, something like that. And then O'Reilly needs probably 3 months to finish the post-production. So the book will be available early next year in the first quarter. Okay? So let's get started. So this talk is broadly divided in 4 parts. The first part is motivation. That is, why should you care about sets at all? I'm going to talk about how sets work in Python, meaning how you use them, from a user perspective. Then we're going to discuss a little bit of some of the ideas of the set API, which can inspire you when you do your own APIs. And at the end, I'm going to talk a little bit about the Dunder methods, the magic methods that make the sets work. And I'm going to do that by showing the source code for a completely different implementation of sets that I've developed, that although the implementation is radically different from the one that Python has, it fulfills the same contract, so it fulfills the same API and can be used in place of other sets. All right, so about motivation. We often need to work on stories that are like this, for instance. Display product if all words in the query appear in the product description, okay? So another language that I've been studying and using recently has been Go. And Go doesn't have sets as built-ins. So I had to write code like this. If you look at it's not a lot of lines, but the cyclomatic complexity of this code is pretty high because there's 2 nested loops, and then there's an if in there. There's 2 ifs. And notice that, so there's a found flag that breaks from the inner loop, and then there's the not found flag that breaks from the outer loop. So it's kind of tricky to write this. It can be better if you split it in 2 different functions. But the thing is, step back and look at that. What if, and the guy says, later I'm too busy coding nested loops. The thing is, you can look at this as a set operation. So you have a set of words that describe the product and a set of words that are in the query. So in this case, the query is coffee grinder, and the description says manual stainless steel coffee grinder. And so this is basically asking whether the query is a subset of the description, right? And if you think about that in a more declarative way, that's better. And sets allow you to do that. Another example, mark all products previously favorited except those already in the shopping cart. So now we have the F set, which is the favorited products, and the C is the cart. And what you have here is a difference, right? Which we would write in Python as F minus C. Okay, so the thing is, sets are really powerful. In fact, I found this quote: "Nobody has yet discovered a branch of mathematics that has successfully resisted formalization into set theory," right? And so logic conjunction is intersection. So the AND operator is intersection, right? The OR operator is union, right? Symmetric difference is what we call an exclusive OR in computer science. The difference is basically the elements of one set minus the elements of the other, right? So in my opinion, people in the Python community don't use sets as much as they should. Put it another way, I've done code reviews where I saw code that could be drastically simplified and also made faster, which is a big win, right? When you get to have something that becomes more readable and faster at the same time, that's excellent. And sets often give you this kind of opportunity, but people missed this opportunity, perhaps because of experience in other languages. I did a little research, and I found out that in some other major standard libraries, there are sets. When there are sets, in the like I said, in the Go language, there are no sets in the standard library. But when there are sets, most of the set implementations available in other languages are very poor, meaning they don't implement a rich API with all the common set operations. So people coming from JavaScript may think of sets. Oh, okay, a set is a way of having unique elements. That's one part of it. But the other part is having those operations: intersection, union, symmetric difference, and so on. So among those languages, only Python and Ruby have what I consider a rich set API. So let's talk a little bit about sets in Python. Ignore the code above. It's just a generator to generate Fibonacci numbers. But the important thing is I have this F set below that I built with a set comprehension. So it's the set of the Fibonacci numbers up to 10 and excluding 10. Another example, the primes. So I have this function that generates primes, and I have the primes up to 10. So we have the F and the P set here, right? So some operations. A basic operation is to determine whether an element is in the set, and we do that with the in operator in Python, which is implemented underneath using the dunder contains method. And this is super fast in the Python standard library because it's implemented using a hash table underneath. I'm so old that actually when I started with Python, there was no set in Python, but we used dicts because of the hash table to emulate sets or to build on dicts to do sets. And then you have all of the fundamental set operations also implemented as operators, as infix operators in Python. So the ampersand is intersection, which makes sense. If you think about the default meaning of that operator in Python is the bitwise AND, and the pipe is the bitwise OR, so naturally is the union, and the caret is the symmetric difference because it's the bitwise XOR, and then the minus is the difference. Okay, so we have these operators as infix operators, and we also have the subset and superset comparisons that are implemented, that are coded in math with those symbols. In Python, we use the less than, greater than, less than, equal. Those comparison operators, they are overridden in sets to do those that kind of superset and subset testing. And you can have complex expressions, like I'm not going to go into detail here, but it's like, so this is a demonstration of De Morgan's law. In line 20 there, it says, right, that the difference between a set and the intersection of the second and a third set is like the difference between the first set, the original set, and the second, and the original and the third, with OR operator inside. Anyway, so this is De Morgan's law, another example of De Morgan's law. Just think about these expressions written without the infix operators, calling methods. That would be really sad, right? Difficult to read. And that's what you have in some other languages that will not be named, that don't have operator overloading. Anyway, but Python, and this is where we learn some good ideas about the API of sets that we can leverage in our own APIs. Because the Python standard library also offers lots of methods for sets. And this is a table from my book. But as you can see, for instance, in the first, so this table is basically split in two parts. The top part is about intersection, and the bottom part is about union. So you have these three different, you have these operators, infix operators, to do intersection at the top, but also you have the dunder methods that implement those operations underneath, and that you should never call. Your own code should not call those methods usually. But what you would call, if you wanted to use the method form, would be s.intersection. But this, and a good idea here, an example of good design in this API is that this is not just redundant, another way of calling, but they leverage the fact that the function call notation allows you to have more than two operands, right? So infix notation is just for two operands. But here you can have as many operands as you like. You have the receiver, which is S, and then within the parentheses you can put as many other things as you want, and then you have the intersection of all of those things. And I'm saying things here because they don't need to be set. They can be any iterables. And that, again, is another thing that they did in the method that is different from the operators. The operators strictly operate with sets. You know, if you use the ampersand form, for instance, you need to do one set ampersand another set. But if you want more flexibility, then you can use the method, and it gives you, it allows you to use any iterable, and it also allows you to use multiple iterables. Right? So this is a great idea of how this API is implemented. Think about that. Often, if you code your APIs so that you get iterables, you make it more flexible, right, for the users to pass whatever is convenient for them to pass into your API, instead of assuming that you're getting a list, for example. But an interesting thing that I talked about in my tutorial the day before yesterday is that maybe you do need a list inside your operations, all right? Or in this case, maybe they do need a set, the way that this method is implemented inside. But it's okay, because the set constructor and the list constructor both know how to handle iterables, generic iterables. So one thing that you can do, which is very easy, is you accept an argument of any iterable type, and then immediately you convert it to whatever you need inside your method. In this case, a set, or in some other case, a list. So that gives you flexibility and also gives you safety, because at the point, if somebody passes you something that is not iterable, it will be easy to debug, because the program will break right there at the start of the method. Does that make sense? So I think this is a good practice. Of course, it has a cost attached to it, because when you're using an operation like that, you're doing a copy most of the time. Python is smart enough that it doesn't copy, for instance, frozen sets or tuples, because they are immutable. So when you use notation in Python to copy those things, Python cheats underneath and passes you a reference to the same thing, because it's immutable, so it doesn't matter whether it's a copy or the same. Anyway, and so it's like this. The other operations, the difference and symmetric difference, are also implemented with infix operators and also with methods. Oh, one thing that I wanted to comment here is also that there are, here I'm describing the full set API, but there is the frozen set, which is a smaller API because it's immutable. So for instance, both kinds of sets have the intersection methods and the infix, the in-place end, which is written like ampersand equals, to change in place the receiver. But the set, which is mutable, also has an update version, right? So that's one difference. And I like the naming that is very explicit in this case. In the case of the union, it's just called update, the version that changes, because that goes with the update method in dicts as well, so it makes sense. But the other operators are like insertion update, difference update, and symmetric difference update. Okay? And then you also have the different sets, or the different tests that return Booleans. And you have a bunch of other methods that are mostly about, that don't have anything to do with set theory in math, but have to do with practical computing, like adding elements, removing all elements of a set, making a copy of it, removing an element, a specific element, iterate over, get the len, pop, which removes some element and then raises an exception if the set is empty, and so on. Now, there is ABCs in Python that define what a set should look like, and those ABCs are like that. So you have the set ABC, the set abstract base class, that has many dunder methods that are basically most of them have to do with the infix operators. And set inherits from container, iterable, and sized. And it's interesting that the set type there, although it's abstract, all of those methods are concrete. Okay? They assume that you have implemented the abstract methods that are inherited from container, iterable, and sized. And if you have implemented those, then you get everything else for free. And in the case of mutable set, you need to implement add and discard, which are abstract. You see the italics there mean that it's abstract. And then if you implement that, you get the other methods for free. Those concrete methods in the abstract classes is what the Python documentation call mixin methods. All right, so now let's talk a little bit about operator overloading. So the idea of operator overloading is that you have those dunder methods that are called when the Python interpreter sees one of those infix operators. Pretty much all of the standard operators in Python are, you can override with this notation, with the dunder methods, except for, I think, 4 of them. The is cannot be overridden, the and, or, and not. The and, or, and not that are written as words cannot be overridden. Because of the way the short circuit evaluation works with and or, it would not be possible to implement them as methods. And the is not overridden because what it does is just compare references, so there's nothing to change there. Anyway, but the implementation of the comparison operator is the simplest part. That's why in my book I cover that first. Because the implementation of, because it does, because there's a symmetry in all of these operators, right? If you ask whether A equals B or B equals A, it's the same thing. And if you ask whether A is greater than B, it's the same thing as asking whether B is smaller than A. So you have the forward method and the reverse methods. There's a symmetry that comes, by the definition of these operators. But with the other operators, the situation is more complicated. Because maybe you have just invented some new type, and you wanted to interoperate with the built-in type. So let's say I just invented a new set type, and I want my set type to interoperate with the built-in set types. Now, the built-in set types don't know about my set type, so they wouldn't be able to do, for instance, the ampersand operation, like built-in set ampersand my set, right? This would be a method call on the built-in set, and it would look at the type of my set and say, I don't know how to handle that. The built-in, the source code of Python doesn't know about that. So the way this is solved is the method that doesn't know how to deal with the other operand returns a special value called not implemented. This is not an exception, it's a special value. And when you return that special value, you're signaling to the interpreter, you need to try something else. And what the interpreter tries is to reverse the operands and call the method with the R prefix. So the AND, if the other AND doesn't know how to do with the argument, then the Python interpreter, then it will return not implemented, and the Python interpreter will call the RAND method on the other operand, passing the first argument as argument. So with this reversal, it gives, the interpreter is now giving an opportunity for my set class to handle the built-in set class. And there's a whole, I drew this flow chart that talks about how this mechanism works, and I think it's really elegant. I think it's really beautiful, the way this works. So one thing that I did was to create an example implementation of a different sort of sets. And my set that I created is actually inspired by a great example in the Go programming language book by Donovan and Kernighan. That's one of the best programming language books that I ever read. The Kernighan is the K in the K&R classic C book, and that's also awesome. And this book is really great. And in one of the examples there, they actually implement a set type for unsigned integers where the values are stored in an array of bits. So they have an array of uints, and each bit there tells you whether there is or not an element there. So the idea is, for instance, in my implementation, this constructor here, I'm constructing an uint set with those numbers, okay? This is represented by this long int in Python. Go doesn't have long ints, so when they did that in Go, they needed to use an array of uints. And that's actually what I did when I first ported this code to Python. But then I realized I was having a case of I was suffering a case of the von Neumann bottleneck syndrome, which is when you think like a stupid CPU that only reads one word at a time. And we're using a high-level language, very powerful high-level language, and we have ints that are arbitrary precision. So those are implemented underneath the covers in C, which is a von Neumann limited bottleneck language, as an array of uints or something like that, right? But I don't need to care about that. So I can represent that set by this number. This is a long in Python. We used to call them longs in Python 2.7. Now we just call them ints. This is so elegant. And that's actually represent that. How does that make sense? It's because it's this bit pattern. Okay? Now I'm going to switch to another slide here that has only one element, which is the last element. So this other set, which has only the element 290, is represented by that huge integer, which has the same number of bits, but all of them are 0, and just one of them is 1. And that represents the value 290, because it's in the position 290. Does that make sense? So that's how the implementation that I did works. And so, for instance, a tricky thing is, how do you represent an empty set? You represent it by 0. 0 is the empty set, okay? The number 0 is the empty set. How do you represent a set with 0? It's 1, because you need to have one set bit to describe a number that's there, right? And this one set bit is in position 0, meaning 0 is in the set. And a set with number 1 is represented by the number 2, which is like that bit pattern, and that's how this thing works. Now, the source code for this is on github.com/standupdev/uintset, and I don't have time to show that now, but what I've agreed with my friends that work for JetBrains is 15 minutes after this is over, I'm going to be at their booth, and I'm going to be going over the code for this implementation. But you can look at it here. It has tests, and it's a complete implementation of the set interface using these crazy mechanics of having bits representing integers. All right? And so that was what I wanted to tell you about. The key takeaways here are that set operations allow simpler and faster solutions for many tasks. The Python set classes are good lessons in idiomatic API design for two reasons. I think it's not easy to always justify operator overloading. Sometimes it's overused. And in fact, there's a key reason why James Gosling didn't put it in Java. I read a quotation of him saying that they didn't put it in Java because operator overloading was way overused in C++, and they didn't want to have this problem. But I think that everybody has learned not to overuse operator overloading. But it's a feature that we have in Python, and it can be used judiciously. And I think sets is a great example of using that in a way that makes sense. Also, I like the fact that they have the other methods that take iterables. And so those are the key takeaways. And like I said, at 11:45, I will be at the JetBrains booth giving an overview of the code. The code is on GitHub, like I said, in my account called standupdev there. And also, at 4 p.m., in the O'Reilly booth, there's going to be a book signing. And the way O'Reilly does is they brought a bunch of copies of my book, I think about 40 copies or something like that, and they're going to hand them out. I don't know what's the procedure for that, but I think it involves handing out little tickets to people that are in a line. And then if you get one of the tickets, you can stand in a line, and you will get a copy, and I will sign it for you if you want. Okay? So those are the things that I'm also going to be doing today. And thank you very much. I'm honored to be talking to you, and I will be hanging around in the hallways as well. All right? Thank you.